Hey guys, welcome to Safi Next. In this video, I will evaluate an integral which has a key role in solving different physical models through the approach of statistical mechanics. The form of the integral is given by I of n equals integral from 0 to infinity x raised to the power n exponent minus x dx, where n could be a whole number or a fraction. However, in the frame of statistical mechanics, this number will represent the number of particles in a thermodynamical system, which is usually very large. So in our case, n will be a positive whole number. Directly solving this integral for very large n through the rules of integration may not be easy. Therefore, we want to find a tractable analytical solution through iteration of different values of n. So let us begin by solving this integral for n equals 0. In that case, it is straight away to write the integral as I of naught equal to integral from 0 to infinity x raised to the power 0 exponent of minus x dx, and everything raised to the power 0 obviously equals 1. Therefore, setting x raised to the power 0 equal 1, I can rewrite the integral in the form 0 to infinity exponent minus x dx. And this now straightforwardly equals minus exponent minus x with limits from 0 to infinity, which putting the limits, I can put this into this one form, and then obviously 1 over exponent infinity is 0 and 1 over exponent 0 is 1. Therefore, the integral reduces to 1, which I can write that in terms of factorial as 0 factorial equals 1. The reason for writing this in terms of factorial will become obvious very soon. So I can write I naught equals 0 factorial. Now let us solve equation 1 for n equal 1. In that case, the integral takes the form I of 1 equals 0 to infinity x times exponent of minus x dx, and using integration by parts, I can put the integral into this one form, where I have treated x as first function and exponent minus x as second function, where in the second part inside the integrand, the derivative partial of x only applies to x. Rewriting the integral into this form, where I have written the first part as minus 1 over exponent of x minus 1 over exponent of x times x in the limit from 0 to infinity, and in the second part I have employed the derivative to x, which is equal to 1, and have rewritten the integrand as exponent minus x. Now substituting the limits, the first part on the right goes to 0, and from the result of equation 2, the integral of the second term is 1. So we can write the integral in the form of this one relation, where I have substituted 1 equals 1 factorial. So I1 equals 1 factorial. Now let us iterate equation 1 for n equals 2. In that case, the integral can be written as I of 2 equals the integral from 0 to infinity x raised to the power 2 exponent of minus x dx. Now employing integration by parts to this integral and treating x squared as first function and the exponent of minus x as second term, we can put the result into this form: minus x squared times exponent of minus x, the limit from 0 to infinity, plus integral from 0 to infinity partial x of x squared times exponent minus x dx. Again, the derivative applies only to x square. Okay, the first term is again 0 for both limits, and the derivative of x square is obviously equal to 2x. So substituting these values, the above equation reduces to the form I of 2 equals 2 times the integral of x times exponent minus x dx. Now, from equation 3, the integral on the right equals 1 factorial. Therefore, we can write the result as I of 2 integral x square exponent minus x dx equals 2 times 1 factorial, which in turn can be written as 2 factorial. Now let us iterate equation 1 for n is equal to 3, and if I substitute n equal to 3, I can write the integral as I3 equals 0 to infinity x cubed times exponent minus x dx. And again, employing integration by parts, I can put the result into this one form. The first term on the right again goes to 0, and the derivative of x cubed equals 3 times x squared. Substituting all these values, I can reduce the integral I3 equals 3 times integral from 0 to infinity x squared exponent minus x dx. And from equation 4, the integral in this relation equals 2 factorial. Substituting that value, I can write I of 3 equals 0 to infinity x cubed exponent of minus x dx equals 3 times 2 factorial, which can be written in the form of 3 factorial. We see for every increasing value of n, the integral reduces to the result of n times n minus 1 factorial. That is, for n equal to 1, we wrote I1 equals 1 times 0 factorial. For n equal to 2, we wrote I of 2 equals 2 times 1 factorial, and similarly for n equals 3, we wrote I of 3 equals 3 times 2 factorial. If we keep on solving for higher values of n, this pattern will continue. So we conclude that in general, the value of the integral in equation 1 can be expressed as I of n equals minus x power n times exponent of minus x with limit from 0 to infinity plus integral from 0 to infinity partial x of x raised to the power n times exponent minus x dx. The first term is obviously 0 for both limits, and the derivative of x power n equals n times x power n minus 1. This substitution lead to I of n equals n times 0 to infinity x power n minus 1 times exponent of minus x dx. According to the previous calculation for 3 different values of n, we can urge that the integral should be equal to n minus 1 factorial. Therefore, I of n equals the integral x raised to the power n times exponent minus x dx should be equal to n times n minus 1 factorial, which can be written in terms as n factorial. On the other hand, we can obtain these values of the integral for different n by using the definition of gamma function, defined by gamma n equals integral from 0 to infinity x raised to the power n minus 1 exponent of minus x dx equals n minus 1 factorial. Using this definition of gamma function, one can easily verify the values of the integral for different iteration for the values of n.